Okay. So, we will be deriving this recursively squares algorithm. So, we have already defined and seen these things actually x n can be partitioned like this. This was where sorry okay. There was one partition, another is d n. As we know, it was d n minus 1, then d n. So, this part you can write as d vector with n replaced by n minus 1 and then current component d n. Another one lambda n it was lambda to the power n this we can write as this is 0 as though this is 0 vector is transpose this much, this is 0 column vector, this is this 1. Okay. So, I am basically partitioning last row is this of which I have all zeros here and just a 1 and last column all zeros here this 1. So, this upper half lambda, lambda square, lambda cube to the power lambda n. So, lambda I can take common. So, it will be 1 lambda, lambda square, this will be lambda to the power n minus 2, because 1 lambda has been taken out, this will be lambda to the power n minus 1. So, that will be this matrix at n minus 1, this is important. What is this at n minus 1? It will be 1 lambda, lambda square dot dot lambda to the power n minus 2, lambda to the power n minus 1, because this index is n minus 1. That is what I have. If I take out this 1 here, all of them have lambda common. If I take lambda out, then this will be 1, then lambda, lambda square, this will be lambda to the power n minus 2, lambda to the power n minus 1. Okay. So, this submatrix will be this lambda n minus 1 submatrix. 1 lambda has been taken out as common. So, this is what these three will be using, and what will be going for? We know W, this is what we have to calculate. From W n minus 1 recursively, not by using the formula, but W n minus 1 also likewise given by something like this. All right. So, from W n minus 1, we must generate W n recursively by simple update equation. Okay. Up till n minus 1, I had only x n minus 1 data matrix, d n minus 1 data vector, and this was lambda n minus 1 matrix. Okay. At nth clock, new data has come x of n. Using that, I build up this x n and add a row. Similarly, new d n has come, so add this extra element at the bottom, and this matrix enlarges to this. Okay. Using this additional information, W n is to be calculated, but not by this formula, but directly from W n minus 1, because there are too many things common between W n and W n minus 1. There is these matrices x n to x n minus 1, Okay, this much is common, x n minus 1 is common, dn and dn minus 1, dn minus 1 part is common, and likewise. This part we have to do. And of course, we are assuming both x n minus 1 full rank, if that is invertible, full rank, so that this is invertible. Okay. Let me call this product A n. So, this will be A n minus 1. So, I am assuming A n and A n minus 1 both are invertible. A n is okay. This is my A n. A n minus 1 is just replace n by n minus 1, n by n minus 1, n minus 7, and both cases inverse is coming. So, I am assuming that they are all invertible, that is small n time index is at least equal to capital N or more, okay, not before that. What happens before that, that we will see later. How to take care of that we will see later. So, this is my A n. So, actually W n is A n inverse, then this part. So, A n, so what is W n? A n inverse d n, right. Now, what is A n? A n was x n transpose so let us first do this part. X n, you remember, was x n minus 1, it was partitioned like this, and this was, it was done in the previous page. So, no need to explain again. So, if I carry out this part, this into this. So, x n transpose, this is x n. X n transpose means first row becomes first column, second row becomes second column, like that, and this last row becomes last column. So, it will be first row of x n minus 1 is first column here, second row of x n minus 1, second column here, dot dot dot, okay. And last row will be last column. So, x transpose n is a row vector, its transpose, this will x n, this will come here, all right. X transpose n is this row. So, when you make a column of it, you have to take a transpose of that, so that is what x n. So, this is x n transpose, and delta n I am reproducing here again. And we had just seen that blockwise partitioning of matrices and their multiplication. So, this will be this matrix times. So, first I consider this part. So, this matrix times this plus this matrix, which is a vector, times this. So, this will be this matrix times this means lambda is a scalar. So, lambda I can take in the front, then this matrix times this plus x n into 0. X n is a column vector, 0 transpose is a row vector. So, column, every element is column into a 0 will give a 0. So, it will be a all 0 matrix. X n is a column vector, 0 transpose is a all 0 vector, row vector. When you multiply, you get a 0 matrix with all elements 0, very simple. So, that when added with this contributes nothing. So, I am not adding that, and then this matrix times 0 column vector, which is 0, plus this column vector times 1, which is x n. So, it will be x n. So, this much, then I have this product times x n, this product times x n. So, now times x n. So, this times x n, and x n I use this partition again. So, that means this submatrix times x n minus 1 plus this submatrix which is column vector times x transpose n. Okay. So, it will be lambda plus okay. And what is this part? By definition, this entire thing is a n minus 1, a n when x n transpose lambda n x n, a n minus 1 x n minus 1 transpose lambda n minus 1 x n minus 1. So, it is actually lambda times a n minus 1 plus this extra component. This is very interesting. This shows how a n, we started with a n, how a n comes from a n minus 1. This is your a n. A n comes from a n minus 1. This is lambda times a n minus 1 plus an extra term. What is the extra term? Current input vector into its transpose. A very simple thing. But I am actually interested in inverse of a n. So, I will have to take inverse of a n, that is inverse of right hand side, and here I will be using that matrix inversion lemma. Okay. So, again I go here, you remember matrix inversion lemma was this. For your sake I am writing once again, assuming A to be invertible and this also invertible, it was this. Times this is what we have derived, and now we have got in the previous page a n equal to lambda n minus 1 plus x n x transpose n. All right. That is, I have a n equal to lambda times a n minus 1 plus, again let us see, lambda times a n minus 1 plus x n x transpose n. But I am interested in a n inverse. I am assuming both a n and a n minus 1 they are invertible. This is invertible, that the total is invertible. That is what I am assuming. All right. So, a n inverse then will be, if I take lambda out, I take lambda common out, plus lambda inverse. Lambda is not 0, it is between 0 to 1. So, lambda inverse no problem. So, this is like your A, this one, alpha is lambda inverse, A is x n, okay, and you have to invert. So, when you apply A in inverse, lambda also becomes lambda inverse, okay, lambda inverse, because lambda also is a matrix 1 by 1 matrix, lambda inverse, which then you write a scalar lambda inverse and can put anywhere either in the beginning or in the end, and inverse of this apply the lemma here. Inverse minus lambda inverse this alpha by 1 plus again lambda inverse. A is x n. So, A transpose, that is x transpose n. A is a n minus 1 inverse A inverse. A is a n minus 1 here, and again small a is x n. This much into this. So, this is A is a n minus 1 here, inverse x n is a, and now bring lambda inverse inside. It becomes lambda inverse lambda to the power minus 2 let me take this to be this. Remember, this is a matrix, this is a column vector. So, matrix into column vector is a column vector, this is a row vector, row into column is scalar. So, let me give this scalar a name beta n. So, notational it will be easier, all right. So, it is lambda inverse into this minus lambda to the power minus 2 by 1 plus beta n times this thing. This is one relation you have found out. Okay. Then, for some algebraic convenience, if I consider this a n inverse multiplying x n, then what happens? If this a n inverse works on x n, that means right hand side working on x n, that means this working on x n minus this lambda to the power minus 2 by 1 plus beta n times this thing into, after this there is x n. All right, this was already there, these 4 terms, after that x n. But then the advantage is I can put a bracket around this, and this is nothing but again beta n, x transpose n, a n minus 1 inverse x n. So, this is again beta n. So, then life becomes simple. It is lambda inverse a n minus 1 inverse x n minus lambda to the power minus 2 divided by 1 plus lambda inverse beta n into beta n scalar you can write first, and then a n minus 1 inverse x n. Okay, let me write down again. This means if I carry out this product, I have from previous page. See, first I find out a n inverse formula, then I am just carrying out one result. If I use a n inverse times x n, what will happen now? Because I know the a n inverse formula. So, I replace a n inverse by this. What happens to that? I will require that later, that is why I am working out. So, it will be lambda inverse, then a n inverse x n minus lambda to the power minus 2 by 1 plus lambda inverse beta n. Times this quantity. This beta n I write first. It is a scalar, I can write in the front or in the end, does not matter. Beta n and then this fella. This is a matrix into column vector. So, this is common, matrix into vector, matrix is common. This is scalar, this is scalar. So, I can just take lambda inverse here minus lambda inverse 2 by beta n divided by 1 plus lambda inverse beta n. These are whole scalar thing multiplying this matrix times x n. And here you see 1 into lambda inverse, that remains lambda inverse lambda inverse lambda to the power minus 2 beta n, that cancels with this. So, what you get is lambda inverse by 1 plus lambda inverse beta n. And what was beta n? Now, you can replace beta n by this thing. This is scalar times this quantity. This entire quantity right hand side, let me call it a vector G n. After all, vector matrix times a column vector, that is what it is. This is a scalar matrix into column vector. So, the vector I call it a gain vector. This is one important result. Another is, now I know G n and I know what is this A n inverse. I can write this right hand side using G n to make it look simpler. So, to do that, first let me write down what was my A n inverse originally obtained, lambda inverse A n minus 1 inverse minus, this is the original form, okay, lambda to the power minus 2 by this into this. This is what we had obtained earlier. Now, this look at this part, lambda to the power minus 2, take one lambda inverse out. So, lambda inverse 1 plus lambda inverse x transpose n A n minus 1 inverse x n, same thing here, and A n minus 1 inverse x n, A n minus 1 inverse x n. So, this part, if I write like this, into lambda inverse. So, this entire part lambda inverse by this into this much, okay, this much. This is nothing but my G n. Look at G n, lambda inverse 1 plus lambda inverse and all these things, A n minus 1 inverse x, this is G n. So, that means this is another interesting result. This is this lambda inverse G n and this thing. So, not only A n comes from A n minus 1, now A n inverse also come from A n minus 1 inverse through this relation. There is an extra term. Okay, this is the most important thing, okay, because in that formula, it is not a n inverse comes. So, W n has a n inverse, W n minus 1 has a n minus 1 inverse. So, I have to relate a n inverse with a n minus 1 inverse, and that is what I have done. Using these results, we will now be generating W n from W n minus 1, that will give us to a recursive relation. That is what we are aiming for, and that I will do in the next class. Please come prepared with this in the next class. Thank you very much.